we missed last week, I just want to take 10 minutes or so and go over and make sure we're all on the same page. First week we talked about what is a variable. And what was the stupid variable that we came up with that didn't make any sense because it didn't vary, but I can ask you and get an answer to?
Oh, no, it was like final grades.
Like a bad variable is something that doesn't vary. We can still measure it, but it won't vary. Like, what planet are you from? Right? So if I were to take time on a survey and ask every person, what planet are you from? I hope I would get the same answer from everybody, right? Earth. So technically it is a variable, but it doesn't vary. And then I remembered, well, wait a minute. We actually have some variables that don't vary. And so I wanted to sort of clean that up and remind you that there are things out there known as constants. And you know these things, right? A constant such as a very famous mathematical number that's not a number, it's a Greek letter. It's delicious. Pi, right? So pi gets to be pi in your geometry of circles because pi is equal to 3.1426 blah, 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 and on and on and on. And pi is famous because of what? Do you know why pi is so famous? Why it's such a magical mathematical number? Because it doesn't end. We have not found the end of pi. When you're saying, Dr. Wood, what do you mean there's no end in pi? There's no end. It goes on and on and on. How do numbers end? Well, think back when you were learning division in like second grade. Division, you're done with the problem when there's no longer a, starts with an R, a remainder, right? So you just keep going until your R is 0, and that's when it's over with. Well, pi is a number. It's not a whole number, right? 3.14256. In all of the decimal places, pi does not have a 0. So there are mathematicians out there just studying where the end of pi is. And so we have computers running, trying to compute pi to the, and we're into like trillionths of digits because there's no end to it. That's a weird, like freaky, magical number, right? Pi is infinite. We also have constants in physics. Anybody recognize this equation, E equals mc squared? It is part of what? Einstein's theory of relativity, which he posits that energy is equal to the mass of an object times the constant, and the constant c is the speed of light, which is really fast, squared. Right? And so we have a, right, this is the speed of light. Right? Light speed, also known as warp in Star Trek parlance. So when they're saying warp 10, they're going 10 times the speed of light. All right. The types of variables that we have, this is where I kind of differ from the book. The book calls these ratio variables, and I like to think of them as continuous variables. A continuous variable type is one where we have a range of numbers, and we want it to be, in theory, infinite. And we have infinity in 3 ways. We can have positive infinity. So space is kind of like positive infinity, right? If you left Earth and headed north, we don't think you'll ever get anywhere. Like, you're not going to fall out of space because we believe space is infinite. if you leave Earth and go south. Right? We also have negative infinity. Does anybody know what the third type of infinity is? We have infinity within. So pi is an example of infinity within. Right? So between 0 and 1, there are an infinite number of numbers. Because you can just get infinitely small and never stop existing. When we measure a continuous variable, we're sort of approximating. So when we do something like temperature, right? Temperature is an approximation of this reality. I don't know if any of you have your phone set up the same way that I do, but I think this is probably an Android default. Yes, I'm not cool enough to own an iPhone. Right? So let's see. Ooh, why was I checking the weather at 5:23? At 11:03 right now is 84 degrees in Conway. Is it actually 84 degrees? Is it 83.6724380? Right? So measurement is in a continuous world dependent upon how it is we measure. Which is funny because with temperature, like 84 is good enough for us. Is it good enough for a doctor? Like you take a thermometer and stick it under your tongue, right? They don't think that like the degree is specific enough. So those always go like out to a digit, right? So you're supposed to be how warm? 98.6. And if you're 99.1 or 99.8, that's different, even though they're both technically 99. So how we measure is very much a choice. Skip that. So continuous variables are variables that have a lot of range. Another type of variable is one that doesn't range a lot. These are known as discrete variables. A discrete variable. And because discrete variables, the numbers do not have space in between them. Between them is nothing. So if I had a number line, there is no such number as 0.57. It does not exist. Kids are a good example of this. How many children do I have? 2. All right, I have John and Abby. I have 2 whole children. If I were to change that number, what would have to happen? I'd have to have another child, which means I would then have 3 children, or I would have to lose one. I got to make a choice. One of them's got to go. Which one goes? If I keep John, the wood name lives on. But he's a pain. Abby's, I got like 10 years invested in Abby, and she's doing pretty good. Maybe I should keep her. But then the wood name might die. Tough decisions. So if somebody says to you, oh, I have 2.5 kids, something's wrong with that person. Either they don't know math, they don't know how to count, they think a dog is like half a kid or something. And if you're one of those people, I'm sorry, there's something wrong with you. A dog is not half a kid. It's a dog. It's a piece of property. You need it if you want to. There's no laws against that. Whole children only, that's an example of discrete measurement. There's nothing in between. Unlike continuous measurement, we're talking exact numbers here. There's no approximation. There's no, well, it depends what instrument we're using, right? Fingers and toes kind of counting. This is exact measurement. These are whole numbers or categories. Now, discrete variables come in three different flavors: nominal, ordinal, or dichotomous. Nominal measurement is when we're taking people and placing them into categories, or they're self-selecting into categories, or we're observing and placing things into categories. We go out to the parking lot, and I ask you to count the color of cars. You're going to name those colors. So what do you call that really dark red? Okay. What do you call like a really deep dark red? Ah, that's what I was looking for. You're wrong. It's burgundy. Right? Somebody find me the difference between maroon and burgundy. Yeah, one's more brownish, one's more reddish, right? We need discrete categories. And you have to name them, and they have to be like acknowledged. But here's the thing about discrete categories. So here's a list of some religions. The numbers that we associate with them for coding and for database management purposes, they don't matter at all. Like, at all. Like, if we wanted to have fun, we can completely change these numbers around. So if I have any good Catholics in here, really what should the number representing Catholics be? You guys never disappoint. Why Catholics? Father, the Son, and the Holy Ghost. Right? The Holy Trinity. Right? Three represents Catholics. All right? Nah, screw you guys. You papists. Mark of the beast. 666. That's the number that's going to represent Catholics. The reason I have to point out so many times that the numbers do not matter is because numbers give us sort of a relativity scale, right? So if you get Catholic as 666, does that mean they're 111 times the Scientologists? If you use the numbers in the data set as like a reference in terms of measuring something else, we're going to have a problem. Because really what the numbers are just categories. They're just really bins that we're sorting people into. If you attach a value to the bins, then it becomes an ordinal variable. We're saying that there's a preference or there's a difference between what the bins are. I used to say that Likert scales are the ordinal variables that you'll see the most. And in looking at the SDA website in the data sets, whether it's the General Social Survey or the American National Election Studies, when you ask people their opinion on something, we tend to give them a scale where they can say they like it, they don't like it, and they don't care. Right? Some measure of ambivalence in the middle. I don't want to offend you, so I won't give you an honest answer. I'll just say, nah, I'm neutral on that. But grades are an ordinal scale. Right? It's my job as a faculty member at the end of the semester to sort you into different bins. All right? And I got to have an A bin, a B plus bin, a B. Really, to me, this is the mode of measurement. But to a student, you don't think of grades as ordinal. You guys think of grades as continuous, right? And you fight for every last point. Dr. Wood, I got an 89.2. Will you round that to a 90? Well, no, I know math. And I know that 89.2 doesn't round to 90, like ever. But I appreciate what you're doing there. You're trying to go from one bin, you're trying to crawl out of the B plus bin, and you think you're crawling into the A bin, but you forgot that for me a 91 is an A and not a 90. And you're like, oh, so an 89, that's like an A then, right? Well, it's close, but you didn't get into the right bin. The term discrimination that we use when we talk about how we treat other people, it's actually a mathematical term. And to discriminate is to categorize and to put people in the different bins. Now, socially, we use the term discrimination to say that you're doing something bad against another person. So the statement, Frederick Wood discriminates, is actually 100% true. Because I take you and I place you into a category. It's actually my job to discriminate. Mathematically. But in a social context, to say that Frederick Wood discriminates, I'd actually like to talk to you about that. I'm interested to hear your perspective on it, and I'd like to let you know that I'm not doing that. Right? He discriminates against, and then insert whatever you think I'm up to. Right? There is a method of analysis known as discriminant analysis. For example, after I give a test, I can run a discriminant analysis on the test, and it can tell me whether or not the people who did well on the test did well on the questions. And it does it for each individual question. And it sort of wants to say, you might want to take a second look at this question. Because the people who should have got it correct didn't, and the people who should not have gotten it correct did. There's something there. It does not discriminate very well. Because the whole point of a test question is to separate people out into these categories. The last flavor of discrete variables has a few names. Dichotomous is the most university vocabulary version of it. We also call them binary variables. And colloquially, conversationally, I call them dummy variables. Now, if it's a binary variable, what are the two options? Because what does binary mean in terms of computer code? No, it does not mean two. What are my two options was my question for computer code. Yeah, 0 or 1, right? So binary code is code that is expressed in a series of zeros and ones. If a variable is a dichotomous variable, a binary variable, or a dummy variable, it means you measure it as either a 0 or a 1. Because the 1 is to denote the presence of a trait or characteristic. It's the thing you're measuring. So if you look in the General Social Survey, the General Social Survey measures sex or gender in a dichotomous fashion because it gives you two outcomes. It is not measured in a binary fashion because the two outcomes are not 0 or 1. And sex, the name of the variable, does not denote the presence of a trait. Male is a binary dummy variable that is also dichotomous. Because male is measured as a 0 or a 1. And does anybody want to guess with the presence of a trait to get yourself a 1? What is that trait? A penis, sure. I'm really tempted to draw a little penis up there, but I won't do that. All right. That's your definition, though. Okay. Can somebody give me an alternative definition for the presence of a trait that makes maleness? An Adam's apple. Sure, I'll take that. Anybody else want to give me a third? A Y chromosome at the 23rd pair. So males have to be XY, females are XX. There's 3. We got any more? We still have all the same number of bones. Testosterone. There we go. Has anybody heard of this runner in South Africa? Her name is Caster Semenya. Yes. What's the story with her? So if you measure gender in terms of genetics, there's something in her genetic code that has resulted in her having increased levels of testosterone. And she doesn't really, she has the appropriate genitalia, right? So in your terms, the absence of a penis, right? So she would not fall under the male category under that way. She doesn't fall under the category in your way either with the XY chromosomes. I can't remember if she's trisomal or not, but there's just something about her code that her body produces elevated levels of testosterone. So essentially, estrogen and testosterone are in a balanced thing, and women produce testosterone, just not a lot of it because they have estrogen. Men produce estrogen, but just a little of it, and much more testosterone, because we have physical, biological gland differences that do this. But men still produce estrogen. All right? She's really fast, because she is, air quotes now, built like a man. And so some people don't think it's fair that she gets to run in a women's race when she's built like a man, even though she's a woman. So there's some controversy here. And the ruling that came out, the International Track Federation said, we're going to measure gender 2 ways. One, biologically, but we're also going to measure it in terms of your testosterone. So she is has a choice. She can keep her body, because we can't give her a new one, but she has to go through some medical procedures, therapeutic processes to reduce the amount of testosterone in her body if she wants to compete. I don't think she's too keen on that. All right. So they're having this discussion now about what is gender. And it's funny because I'm a social scientist, right? I teach about how to measure things. And we have people out there who are very insistent that gender is binary and there are only 2 options. And I'm like, tell me how you measure gender, right? If there's only men and women, how do you account for the fact that continuous variables exist? Well, if you're going to measure it by terms of testosterone, guess what? Men have different levels of testosterone. I know this because I watch TV and they tell me that there's this thing out there called low T, and I should talk to my doctor about it. Because there's a solution for low T. I can shoot myself up full of testosterone every day if I want. Or I can get a patch. The problem is if you wear the patch, nobody can touch you because you're dripping in testosterone. Yeah. So as a social scientist who understands and teaches and studies this idea of measurement, I know that really what we're doing when we engage in measuring is we're making choices. We're making decisions on how to measure a concept. And we have options. We came up with, 3 or 4 different ways to measure gender in a binary fashion, and we didn't even talk about how we can do categories. We can do an ordinal gender scale. I strongly am a male. I am weakly a male. I am gender neutral. I am slightly female, and I am strongly female in a Likert scale. We can do that. In fact, we do all the time. It's called bullying. We actually have those scales pretty well defined in society. Or we can measure in a continuous fashion. Yeah, you lean male, but your testosterone is, and then actually have a number. This many parts per million in your blood. High-level athletes, we have this perception that a lot of times it's just because they train a lot. And so there was this pop science book out a few years ago that said you need 10,000 hours. You need 10,000 hours to become like really good at something. And they're basically saying you need to work hard and practice if you want to be an Olympic swimmer. No. Michael Phelps, the all-time winningest Olympic swimmer, is just a lucky bastard. Because his body produces more red blood cells in its blood. His blood is literally thicker than mine. I can practice more than him, but because his body carries more oxygen in its blood, he has to breathe less than I do when we swim. Also, he's 6'6" and has like size 14 feet, so his flippers are bigger than mine. The thing about variables is that we make decisions about them. So when you're looking at the SDA website and you're looking at data, you can change it. You can take a variable that they measured one way and change it into a different type of measurement. So we can have something that starts out as continuous, like a grade on a test that ranges between 100 plus some bonus, depending upon your instructor, down to a 0. And what does the university make us do? The university makes us change that into an ordinal variable from A to F. Or a dummy variable which is really, in different ways, some people are concerned about. I'm not really concerned about my grade. I just want to know, am I going to pass this class? Or if it's a particular class, am I going to get a C in this class? Because C's get degrees, right? What you're doing is moving. You don't know you're doing this because I haven't pointed it out. I haven't taught it to you yet. What you're doing is you're engaging in social science research and you're reclassifying variables. And you can move from continuous to ordinal to dummy variables. very easily. You do this in real time in conversations with your parents. So how are you doing in math? I'm passing. You've given them a measurement. No. How are you really doing in math? I'm in the C range. How are you doing in math? I have a 71. Oh, you need to work on that. You just, in real time, reclassified that variable 3 times. You measured it. You gave the preference. I want to talk about it this way. Parent said, no, I want more information. Okay, I'll give you more information. I'm passing and I'm getting a C. What kind of a C? Like an almost plus or a barely a D plus? Is it a high C or a low C, or where are we? Are we close to going down into the D categories? Or you could do it the opposite way. I've almost got an A. Okay, what do you mean almost got an A? Like, how close are you? This is the discussion I have with Abby. She's like, well, I have an A. Okay, that's great, but it's only a 97. Hello? Man, why are your teachers doing to you that making you think that a 97 is good? I got 50 students that would be like, yeah, 97. We're really messing up kids these days. All right. So that's my now 20 plus minutes on measurement. The reason I needed to do this is A, I don't trust that you actually watched the video over the hurricane break, because I didn't do any work over the hurricane break. And 2, you have to be comfortable with this, because you passing this class is dependent upon demonstrating that you can manipulate data. And I need you to understand that you already do measure data. You just don't think of it that way. Now that we have the same vocabulary, and I say ordinal, and you think, oh, ordinal, order, lettered grades or categories. I got that one. Now we can talk about how we can take vast piles of data and summarize them using statistics. So today, let's do some math. And the type of statistic we're going to talk about today are known as measures of central tendency. Sounds painful, but it's not. Central tendency, aligning your chakras, right? Finding a calm space, centering yourself. That's what we're doing. A measure of central tendency is a statistic that identifies the center of a distribution. Here's the thing. We're going to start thinking about our data in terms of having a lot of it. Let me tell you a stupid story. So Abby's a Girl Scout, and my wife is the cookie mom. So in February, if you want some Girl Scout cookies, come find me. Because in February, I'm going to have 5,000 boxes of Girl Scout cookies in my garage. Yeah. My wife's the cookie mom, which means I'm the cookie dad. And I have defined my own responsibilities of the cookie dad as the person who deals with the money. I learned something valuable. You should not rely on banks to count your money, because they do count it. But when you walk into a bank with about $2,500 in small bills, and you hand them a bag and say, I'd like this to be deposited, they won't take it unless you tell them how much you think is in that bag. Please, deposit this. And they're like, deposit what? The money. What money? This money. What money? They wanted the number. They didn't want to touch the money until I told them how much money was in there. Does that mean they were going to then just take my word for it and put the money bag underneath the desk and be like, all right, we have it. Here's your slip. No. They still have to count it, but they want to make sure that I know how much money's there, so then I can't accuse them of stealing my money. Because I thought the bag had $3,000 in it, and they counted all, and it was only $2,500. If you've never had this experience before and you've been given a bag of money that has been lorded over for the weekend by 7- and 8-year-old girls, let's just say it's an experience. And so I go home with my bag of money that they would not take, and I now have to count the money. So I've dumped a pile of money on the kitchen table. What is the first step? If I'm smart, I'm going to sort all this money. I hate change. I don't know why people do change. We should get rid of it. So that's the first step. Good thing. My kids can recognize numbers. Even John knows what the difference between a 10 and a 20. Come here, kids. Kids sort all the money. Good job. The next step is to count how many of each monies I have. Other good thing, kids can count to 10. So there's a stack of ones this tall, like 5 inches tall. John, give me piles of 10. Okay. He can count to 10. Trust me. Counts out stacks of 10. Good. I can count stacks of 10. I have my numbers. Bound all the money up. Go to the window at the bank. Put it down. Deposit this money, please. Slide my frequency distribution table to the lady and say, it is $2,387.35. I went 4 for 4 last year in cookie season. Nailed it. The exact same number. Why? Because I treated it like a data project. She told me, come back with a number. And my training says, I know how to do this. I'm going to create a frequency distribution table. I'm going to categorize the bills. Fortunately, they're already categorized for me. And I'm going to count how many of each I have, and then multiply through and add it up. Now you're like, duh, that's how you count things, idiot. But no, stats professor, frequency distribution table. And so that's why I got my kids saying, all right, well, what's the f of x? And they know what I'm talking about. All right. So which one is the mode? Mean, median, and mode. It's the one you have the most of. So John, what do we have the most of? Well, when you're doing Girl Scout cookies, the most is 1s. Yep. You want it to be 20s, but no, it's always 1s. So I'm the guy that goes to the bank with hundreds of 1s. Because of that $2,000, about half of it is going to be 1s. I like 50s and 20s because they're small. They're like this much, a lot of money. Don't want to get robbed and be the guy with the duffel bag of, money coming in the bank. If we do a very silly line chart here, we can easily tell where the mode is because it's the peak. If this was a bar chart, we would just look for the tallest bar. Bar. Right? Easy. The mode is just the most frequent. It's the highest number if you have a frequency distribution table. If you got a pile of bills on your table, it's the tallest stack. That's the mode. So the mode just involves counting. How many of each do you have? The median is a little bit different. You've heard of a median before. So if you're driving home, what's the median? Well, A, it could be a physical concrete barrier or steel barrier, right? They could actually build a median. But if they haven't built something, what's the median of a road? The yellow lines in the middle. That's the median of the road. It's the middle of the road. For us, if we have a pile of variables, it's the one in the middle. It's the value of the middle variable. Now, in order to do this, to calculate the median, first you have to take your data and you have to sort it. I lost $5 on the Browns, I pushed on the Cardinals tie, and I won $10 on the Patriots. Okay, those are the 3 outcomes from my betting this weekend on National Football League. I have now sorted them in order. -5, 0, and 10. What is the median? 0. I have 3. Three outcomes. 3 plus 1 is 4. 4 divided by 2 is 2. 1, 2, 3. This one. That's the median. First step, always sorting your data in order. Preferably from lowest to highest, but it works both ways. So when you do section exercise number 3, and I ask you to calculate the median, what's the first thing you should do? Sort. If I was evil, I would give you like 7 or 8 numbers and mix them all up. And then I would give you an answer choice that is the median of the unsorted variables. That's what I did. So just letting you know right ahead. Right? If you skip step 1 and you don't sort, you're going to get the wrong answer. Four scores, nothing, just 4 numbers. What's the median of that? Well, if you have 4, 4 plus 1 is 5. 5 divided by 2 is 2.5. What's the 2.5 number up there? Actually, all you do is find the average between the 2 middle numbers. So this is the spot right there, but there's no number there. There's the space in between the 3 and the 7. So to calculate the median when you have an equal number of observations, you're going to take the 4 divided by 2 score, which then is the second score. You're going to add the 4 divided by 2 plus 1, the third score, and divide that by 2. So 3 plus 7 divided by 2 is 10 divided by 2. So the median is equal to 5. Hardest thing with calculating the median, 1, remembering to sort, and then 2, figuring out if it's odd or even. How do you know if it's odd or even? You have to count how many observations you have. Anybody having like a really harsh like 3rd grade flashback? Because that's when you learned this. I know because Abby was in 3rd grade last year and we did mean, median, and mode. Back to our example from the bar or whatever this is from the book, estimated brain power. So if you ask somebody how much you think of your brain you use, they'll repeat this urban legend that you only use 10% of your brain. That's not true. So I can't cut 90% of your brain out and then you still be okay. Like, you're going to be really messed up. Let's ask a question of people that we actually don't know the answer to, and then we'll just make up something. So, the last one, the mean, also known as the average. Here's the thing about the mean. You've learned about what an average is, again, since 3rd grade, probably even before that. And that's actually really good for me, because we're going to base pretty much everything we do in statistics and probability theory off of the existence of the mean as a measure of central tendency. So, how do we calculate the mean? Well, first of all, the mean is represented in our data as x, which is our variable, bar. You put a line over it. I got no story as to why it's a bar instead of a squiggly line or a hat or anything else. X bar. That sigma there, first of all, it's a sigma if you're not Greek, either ethnically or socially Greek. That 3S looking thing, that's a sigma. That's actually a capital sigma. And in math, it's a way of saying add. It's known as a summation sign. Summation, sigma. Right? So you're going to sum. What are you going to sum? Well, when you see it plain like that, that means all of them. You're going to add up all of the x's. So if I'm going to take the average of those last 4 numbers, 0 plus 3 is, thank you, plus 7, plus 9. Okay, so the sum of x, if x equals 0, 3, 7, and 9, the sum of x equals 19. 0 plus 3 plus 7 plus 9. Let's check our work. What's 7 plus 9? What's 16 plus 3? What's 19 plus 0? Check your work. Sorry, I do this with Abby. She hates it. All right. N. What is N? That's an N. It's not new, N-U. It's just N. N is the universal math notation for how many you got. The number of observations. How many observations do we have? 1, 2, 3, 4. $19 divided by 4. Shit. Thinking 4/5 to get to 20, but should have been thinking 3/4. Didn't do my remainder. That's why you always show your work, so you don't look like an idiot. All right, so the mean of this set of values is 4.75. That's x bar. That's our measure of central tendency. Wait a minute. If we look at this chart, for the example from the book, the mean for how much of your brain do you use, according to Howard, is 22.89. Now the mode, is here. I'm going to take his word, but the median was at the same place. So the median and the mode are here at 10%, and the mean is at 22.89. So we have three measures of central tendency, and in this case, only two of them agree. Why? Mean, median, and mode are the same type of measure. They're all measures of central tendency. So here we have a data set. We calculated the mean, the median, and the mode, and we got two different numbers for three different statistics. Why? Well, really simple answer to this. All three measures are looking at something different in our data. They're not capturing the same thing. So the mean captures all of the data. Remember that sum of x? We're taking every single observation, every single person in our data set, every single measurement that we have, and adding it all together. So when you have data that is, the term we use, skewed, we don't have nice, evenly spaced out data. The mode tells us that most people said we use 10% of our brain. The median said half the people say we use 10 or less or 10 or more. And the mode says, well, the average is actually 23. And the reason is because the mean is taking into account the relative position of what the answers are. Okay, mode is just counting the most. The median is just looking at the middle. The mean is saying, let's see how all of these are contributing. Because the mean includes all of the, I almost said value or weight. The mean includes all of the measurements. What we have is a point at which not half of the values, plural, but half of the value is above that point and below that point. Okay. So here's a way to distinguish between the number of values, that is the median, and the weight of the values, that is the mean. So neat little thing about the mean is it's actually a balancing point. Here's a set of 9 numbers. The average or the mean of these 9 numbers is 3. So if we look at the difference of each of our individual numbers from 3, right, subtract x bar from x. What is the weight of our negative numbers? Well, let's look at the negative numbers. What's the first negative number? 1. What's the next negative number? And what's the last negative number? Let's do the positive numbers. Your turn. Go down the list and tell me the positive numbers. Positive numbers of the difference, the last column. Yep.
3.
Nope, you skipped one. What's above the 3? That's not a positive number. So we go down the list, we got a 1. We go down the list, we got another 1. And then we have 3. Right? So we have 5 positive and 5 negative. It's balanced. It's balanced around 3. It's centered around 3. He even did like a little teeter-totter. You got 5 blocks on that side, you've got 5 blocks on the other side. The sum of the differences from the mean should always equal 0. I gotta say, this is the shit that makes me love math, right? You can take something like the mean and you say, if we know this, what else do we know? All right? So I know that because of the way that the mean is calculated, that the sum of all of the individual differences from the mean will always have to equal 0. Right? And here's the thing. I'm a social scientist, right? I study people and how they behave. I got nothing that is certain. I can tell each of you the same piece of information, and you can all go out and do something completely different. But with this, I have an absolute, right? I've got a rule. I know that the sum of all the deviations from the mean are going to equal 0. Why? Because the way the mean is constructed. And this is how, over the last, 500 plus years, we've actually built up statistics by taking things that we know that are certain to be true and then applying them. And through every time we calculate the mean. I did this to Abby. Oh, man, I'm such a bad dad. Like, I am the wrong parent to come to talk about math. Because I love this stuff. And I'm trying to show her, hey, you want to see something cool? And I show her this, and she's like, that's not really all that cool. Why would I want to do that? Well, you can check your work. Well, I have the answer. Like, the calculator did the work, Dad. Oh, I haven't quite gotten that spark in her. Getting there. But isn't this really cool? No, not at all. Am I done yet? Oh, failed. Okay. A couple more things about how we're going to interact with this. So, week 1, we had this conversation when we were talking about variables and what it is we're measuring. It turns out when we're doing notation like this, that we actually care about whether or not we have a sample or a population. Because the notation is completely different. Sorry. Again, I didn't create this stuff. You got to blame a bunch of dead guys. So when we talk about the mean in terms of x bar, when we do that, we're referring to a sample. Size of your feet? Shoe size? 11. Anybody got a bigger shoe size than 11? Got like a 13 in here? What do you guys got? 12? No 13s? No offense, but the Tuesday class, I had 3 guys with 13s. Like, you guys need to step it up a little bit. Nobody's got like freakishly big or freakishly smaller feet. Ladies, anybody here got a big shoe? How about a little shoe? We'll go in the opposite direction. No? See, in the Tuesday class, I had these guys. They're about 13 size feet. You imagine what it's like to buy shoes if you have size 13 feet? You think it's expensive, but that's not the biggest problem. You know what the biggest problem is? You can't find shoes that are that big. You go into a shoe store and you're like, show me the size 13s. And they come back with a box. And they're like, here's your brown shoe. Why is that? Why do they have such a hard time buying shoes? Because it's above the average, right? Here's the thing. Nike or Under Armour or Fluvog or whoever's making shoes, when you make a shoe, you have a hope. And your hope is that you sell that shoe. Okay? So when Nike goes out and makes shoes, how many people in the world are going to buy a size 25 shoe? One. You know what his name is? Shaq. Dude has a size 25 foot. Shaq can't walk into a Foot Locker and be like, hey, you got the new Nike whatever? Because they don't. They don't have his shoes. They don't make a size 25 shoe. Because what would happen if Nike did make a size 25 shoe and made like 1% of its inventory in size 25 shoes? It's going to lose money. It's not going to sell it. It's just going to sit on the Foot Locker shelf, probably used as like a doorstop or something. Okay. So if you're a guy, and I verified this with the three gentlemen in Tuesday, they got size 13 feet. When they go to buy shoes, they have like three options. They got a black one, a brown one, the gray one that nobody buys, the thing that's both black and brown, and then this really weird blue suede thing that nobody buys. And they're like, yeah, we really just buy whatever is available. And I'm like, I get that, because I have wide feet and people don't actually make wide shoes. So I went to the shoe store over the tax-free weekend and I had two options, so I bought them both. I have brown with laces and brown without laces. I have no choice whatsoever. And then there's some of you people that are in like the shoe sweet spot, right? You're like at an 8. Yeah, are you blessed with average sized feet? And you can find a random pair of shoes on the side of the road and you're like, oh, they fit. Like the world has been blessed upon you. You know why? Because you're the middle, right? In this distribution that's out there. You're the middle. Theoretically, and again, because we know one thing to be true, we can make inferences and therefore believe another thing is true. We make this same inference about means and the difference between the sample and the population. And we'll get into this later in the semester about how this actually works. But here's what Nike does. When Nike is trying to figure out which size shoes to make, they really need to know which size of shoes sell. So they look at their inventory. They look at how many pairs of shoes go out and what percentage of those shoes get returned. Right? If they have their own stores, like outlet stores, that's great because they don't even have to like ask Foot Locker. They can just hoard their own data. Or, even better, they could buy data about spending patterns from other people or get you to freely give it to them. So this difference between a sample and a population is why we have things like rewards programs at stores. or apps where you freely take pictures of your spending receipts and send them off to somebody else to sell. So there's an app out there called Ibotta that your mom probably uses when she goes to Costco. So she'll save 25 cents on orange juice. And in order to save that 25 cents on orange juice, she takes a picture of her Costco receipt and gives it to Ibotta. And now Ibotta knows everything your mom just purchased in her shopping trip. You remember when you were a kid and you did the, you cut out the box tops for education? Guess what? They don't really exist anymore. There's an app now. And I have to take a picture of the granola box and my entire receipt so that like the school can get 10 cents. Why? Well, they got to get that 10 cents from somewhere, and what they've done is become a data mining company. They're collecting your data. There was a company called MoviePass. MoviePass was a great idea that nobody ever thought could work, and in fact it didn't. It's like a subscription like Netflix, but to go to physically to a movie. So you pay MoviePass $20 a month, and every time you go to the movies, you check in on your phone, and they load your debit card, your MoviePass debit card, with whatever it costs at that theater. So let's say you go to a matinee, they load it for the $6.86, and then you pay using your MoviePass card. Well, if you see more than your $20 a month, MoviePass has to eat that, right? Because they're actually physically paying the movie theater when you swipe your MoviePass card. Here's the thing. They thought they could make up that gap by selling all of the data on your phone. Because you had to download the app, you had to have location tracking on, and so they thought they could sell information about moviegoers to the studios. They can see what stores you shop in, they can see where you go, depending upon what accesses they had. They could look at your online spending, like they could look at your cookies, they could see what websites you go to. They essentially had your phone. And they're pretty much going to go out of business. We want to know as much as we can about the sample of people out there so that we can then infer about the population. So Nike can make sure that they're not losing money on size 25 shoes. And that's going to be important to companies, but it's also important to us because we do public opinion research as social scientists. If we want to say the American public feels about abortion, we don't want to have to go out and talk to every person in the American public. Have you met those people? You don't want to talk to them. But also we don't have the time and money to survey 330 million people. So instead, we find a sample. And we calculate what our sample means are, and then we use that to make inferences about the population. I'm out of time, but essentially what we have here and the difference between mean, median, and mode is some of them work well for one. So mode works well with nominal data, and median works well with ordinal data, but really the mean is the best, and it works best with all sorts of data. And so take a second look at that, and I will see you next week.